Hello everyone, thank you for joining the webinar. Welcome. Today we're going to talk about copper elements and hopefully how you can maximise the performance and productivity of your furnace. I'm going to tell that from basically the point of view where I work, which is Glencore Technology, and I predominantly work on isosmelt furnaces. So the overview of the presentation is, let's talk about what is furnace productivity and furnace life. What do they mean? I'll introduce you to who is Glencore Technology. Some of you know us, some of you may not, so I'll just explain that. I've coined a phrase here, the isosmelt group of furnaces. I'll explain what that is and why I've done that. Let's look at why does industry use copper elements, and I'll talk about our experience in the isosmelt group, copper elements. And then I'll typically run you through how we implement a project supplying copper elements into a furnace. And then we'll stop for some Q&A. So first things first, furnaces are built to produce metal or slag of some sort. And the productivity is proportional to their throughput capacity. How much can you feed the furnace? How much can you digest in the furnace? How much can you tap out of the furnace? And also proportional to the plant availability. So for example, a furnace that's available for 90% of its operating time is going to produce more than a furnace that only has 70% plant availability. So they're the two key things for furnace productivity. And then life, that can apply to component life and furnace life. And we normally measure furnace life in campaign life, which is the period from one furnace rebuild to the next. So a long component life will generally produce a long campaign life. That results in high plant availability and high productivity. And then what your bosses really want to know about is that that's higher revenue and higher profits. So there's the magic formula. You want high plant availability to get high productivity for the reasons I just mentioned. So let me explain. I coined this term isosmelt group of furnaces. That's not a thing we market. I used it for this presentation because it lets me describe where we've come from in terms of using copper elements. And that story over 50 or 60 years has involved many people, many types of furnaces, and many decades of experience and different sites. So I'm really talking about what you see on the screen here, and that's predominantly where we use and developed our copper elements in the Mount Isa site, but also where we tend to sell these into projects in the present day. And that is isosmelt furnace, top submerged lance technology, RHF, or rotary holding furnace, and blast furnace. So isosmelt furnaces have been around for 30 plus years. And this is a global map showing the sites which have taken up the isosmelt technology. There's 25 sites there, and we have supplied that technology in the form of projects onto those sites over the past 30 or so years. And basically those projects have used the design methods and the project methodologies that I'm going to describe today. So why does industry use copper elements? Well, in the furnaces, there are critical areas where extreme conditions prevail. And often this is a bit too much for traditional materials. So that can result in high failures and low reliability. The copper elements, though, offer superior life in those extreme conditions, reduced component failures, and reduced downtime. So that's better furnace availability and better productivity as a result. In our own group of copper elements, we use the copper elements. We were not the people to invent these. We started using them maybe 50 years ago, and they've developed since. Though we've always had a furnace operational challenge to overcome when we've deployed copper elements. And in fact, isosmelt technology would have struggled to get off the ground had we not developed roof blocks and splash blocks especially. So these are focused very much on functionality and serviceability, manufactured to suit real world conditions, provide robust performance and high plant availability. Those are the principles that underlie our projects generally, and especially apply to copper elements. So again, there's the magic formula. People want that high productivity because your budgets and your viability as an operation depend on that. I read in the literature as early as the 1920s, there were records of people experiencing trouble with tap holes and experimenting back almost 100 years ago with cast copper tapping blocks. And I'll talk a little bit about tapping blocks, especially in this presentation. I don't have time to talk about all of them, but if you do have specific questions, please put a question in the chat, or if it's a really specific question, you can book a hot seat session and we can chat over Teams. So let's look at the copper elements in that group that I defined, the isosmelt group. So in the isosmelt, there are roof blocks, splash blocks, bath blocks or sidewall coolers. Those are used more in the isoconvert technology these days. They were used extensively in the early days of isosmelt, but it's quite rare now. Tapping blocks, tapping launders. In the RHF, there are lip blocks, curtain blocks, dipping ports, burner ports, pig iron ports, and in some mat spouts, slag spouts, and in some cases end wall tapping blocks. And in the blast furnace, elements have been deployed as sidewall jackets, end wall jackets, and weir jackets. So I'll just show you some photos of those things in installation. They're usually quite hard to see once the furnace is in operation. And I'll start to talk about where our technologies developed from. We didn't invent copper elements, but in Mount Isa, northwest Queensland, is where next year will be 100 years since discovery and start of planning operations up there. So that's the site where these furnaces have been operating for many, many decades. And the plant owners have always wanted to have better productivity and availability. So that, because of its remoteness, there's always been a strong engineering culture. Most of the time of the existence of Mount Isa, it's been in-house engineering resources. So as a result, engineers are in the plant every day. They're facing plant owners and tend to have a high degree of accountability. And project team structure tends to be based on collaboration and making solutions that work. This is where Glencore Technology grew from, and this is a big business culture that we continue with today. So the other part of the story with Copper Elements is CRL in Townsville, or Copper Refineries Limited. It was set up in the 50s to refine Mount Isa copper into LME grade copper. And it was also the site of many innovations. Isa Process was marketed out of here, and these days Isa Kid, which is a collaboration of Isa Process and other technologies. Significantly for copper elements, this was the site where our copper elements for Mount Isa were first made. So Townsville was able to make the copper cake that was necessary as a product, and then cut and drill and plug copper blocks from that copper cake, pure copper. So the project culture that I described is described on this diagram. So it's a strong collaboration of process, mechanical and operations, a healthy blend of skills and expertise in that group, clear and shared goals and attention to detail for projects, and systems with seamless operation, creating solutions that work. And that's the success zone right in the middle of there. You need all of those parties present and communicating to get that success. So I just wanted to show you a timeline of copper elements, how they started and where they've come from. Up the top, refractory and water-cooled steel jackets have been around forever and will have their place forever. But in these more critical locations, it's the copper elements that that really stand up and handle these situations. It was in the late 60s that uncooled copper blocks were first used in our reverberatory furnaces in Mount Isa. And it wasn't too many years until Townsville was making us some of those drilled and plugged elements, especially for tapping blocks and for burner ports. They were introduced in the early to mid 70s. And those have undergone generational change ever since and improvements along the way. And then in the early 2000s, we turned a lot of attention to going to cast copper with cast-in piping, because that offered us superior benefits, and I'll describe a lot of those benefits later. So just looking at the various technologies which I showed on that timeline, from refractory at the top, cooled steel jackets through the copper products. Generally here, what you see is lower cost at the top and lower reliability, and higher cost at the bottom and higher reliability. So it's really a matter of choosing the situation and the solution you want to provide to achieve the productivity that you're after. Because really every smelter operates its own way. They have their own choices, and it's making all those things work together. So I said I'd talk about tapping blocks. This is a good opportunity. So in a refractory version of a tapping block, traditionally the tap hole would consist of a bricked arch. So that would require specialized skills to lay that bricked arch, special shaped bricks, time-consuming process to lay that. And then the brickwork is subject to thermal stress, thermal shock, and erosion, and mechanical stresses from barring or mechanical damage, from barring or oxylancing, or even perhaps tapping machines. So they're pretty subject to failure, and they're very difficult to fix when they go wrong. So that can definitely have a big effect on your output of your furnace and its productivity. A cast copper tapping block, though, by comparison, it's much stronger and tougher. It can handle the thermal stresses and thermal shock, because it's operating at a much lower temperature. It's got the water to reduce the copper temperature and deal with those things much better. Similarly, with the mechanical stresses, it can handle that much better because it's stronger and not as prone to damage as the brittle refractory. I must say, though, that almost nothing can stand up to the to oxylancing, and that's an issue that each smelter must have to look at in terms of its overall operation. The copper blocks also give a good opportunity to control freeze zones. So first of all, if something does try to leak, there's a good chance of the copper block arresting a leak. It's very common for furnaces to have breakouts and drop several hundred tons of metal on the floor. That's not a situation any smelter wants to see. In addition to that, it'll form a slag coating on the inside of the tap hole, which actually helps to reduce the heat load on the copper, and again, make life easier for the copper element. Copper blocks are also easy to change out from the outside of the furnace if something does go wrong. But in Isa smelt furnaces, we make our tapping blocks in two pieces, a small outer piece and a large inner piece. The outer piece tends to take all the damage from the mechanical damage and erosion or oxylancing, and it's easy and quick and relatively inexpensive to change out. But the inner blocks virtually need no replacing from one rebuild to the next, and sometimes they can be refurbished as well. So I'll talk about the early designs, just a couple of snapshots of where we came from and where we are. So you can see in the photo there a big slab of copper cake in the Townsville works. So that's being prepared to cut into blocks, make drilled and plugged blocks. And in those days, typically our cooling fluid was always water. Down to today, so there's a lot more strings to our bow. So with over many projects and many supplies for customers, we've listened to the wants of users, taken on field experience as we install and commission these things. And all of those versions have been updated over the decades that they've been in existence. We tend to favour cast copper these days because we can make much more complex shapes like the one in the middle there, the tapping launder. And it also gives opportunity to have cast-in cooling channels, and there's a lot of advantages to that as well. We have a variety of cooling channel materials to choose from, and the cast-in channels provide superior leak resistance. You don't want water leaking in around furnaces because it can be a great safety risk. There is a variety of cooling fluids available, although we do very often use water. We have developed very robust design practices based on real-world data and tested in operation. We've also done advanced inspection and testing, and then we've done a lot of peripheral aids and programs, such as for shipping, installation, commissioning, and operation. And I'll talk about that in more detail in the project description. So I'm sure most of you have used copper blocks, but if there's anyone who hasn't and you're thinking about it, you really want to weigh up the benefits, the affordability, the risks and the rewards. You need to have a cost benefit analysis. So you want to look for, if you go for a quality design and get this done well, what you'll achieve is long life, possibly greater than one campaign. You'll have low maintenance and reliable performance, so improved plant availability and therefore productivity. You'll have good control of those freeze linings, and I'll explain the benefits of that. You'll be looking to refurbish where possible to save replacement cost. You'll be looking for good leakage control, good compatibility with furnace linings and adjustable cooling rates. If you want to talk about any of those, as Stuart mentioned at the beginning, you can book a hot seat session and we'll have a chat on Teams with you. You also need to be aware that to get the rewards, you need to take risks. And the way to deal with risks is to know them and to manage them properly through good design. So you want to avoid overcapitalization. You can spend way too much if you don't choose the right areas and the right way to deploy these elements. You want to avoid excessive heat load or undercooling, which can result in damage. You want to know what happens if you lose water flow or reduce water flow. That can create damage or worse. And also you want to be aware of acid condensation because that can form sulfuric acid in the furnace atmosphere if you're not designed properly. You want to avoid in-furnace explosions due to water leaks, and you want to avoid steam explosions in piping. You also want to avoid improper water quality because that can deteriorate performance and create problems, including safety problems. So again, if you want to talk about those things, you're welcome to book a hot seat session with us. So let's talk about the successful implementation, and I'm going to describe how we go typically about this in an isosmelt project, because we do lots of those. You saw there were 25 of those around the world, and we've done this lots of times and it works well. So I'm going to describe 3 stages of that process, and that's quality design, quality manufacture, and quality integration. In those 3 stages, there are a total of 10 steps that we take to get that good result. And we want to encourage that project culture and get the parties in the success zone, including parties from the plant owner and the customer, because that's important. So the first step is to understand the site and operational requirements. So this needs to work in an existing plant. It will have existing practices and existing procedures and existing systems. And so we want to understand those and see if anything needs to change to work with the new technology. but we also need to look at the new element and see how it interfaces with those systems, with other equipment around it, and with the people who are working around it. So that is something that needs to be understood to set up the project parameters. And then in the design stage, step 2 is process design. So our process specialists will look at the furnace operating conditions, look at the temperatures, look at the contents of the furnace, look at the fluid flow paths, look at the gas flows, especially with relation to acid dew point, look at the freezing, the liquidus and solidus issues, and the frequency of use, and come up with the design parameters needed to make something such as a tapping block work well and reliably. In the design stage, step 3 is the mechanical design focus. So this is where we really get down to the nuts and bolts. So we maintain a customer focus based on the information gathered in the previous 2 steps. We refer to that 50+ years of real world experience that we've developed since ISA first started using these copper blocks. We know the risks, and then we design and operate to manage the risks. And it's important that design and operation go hand in hand there, because they need to work together to get that very best result. And they're both aiming for those solutions that work, if that's the case. We need to understand the operating environment. We need to design within predictable limits. We need to simulate operating scenarios, such as you see in the FEA there at the right-hand side. We need to make things practical to manufacture. Some of these castings are very large and very heavy, and they take a lot of expertise to make without defects. So that's an important issue. And you need to consider the integration issues, and we'll talk about that a lot more further down as well. Most importantly, you need to communicate a lot and bring all the parties together into that ISA Smelt success zone. The fourth stage of the fourth step of the design stage is to integrate into site and systems. I won't read all of these here, but it's pointless having a copper element that works beautifully, but if the water supply is not reliable, it's not worth much. So all of these issues need to be inspected so that flow is guaranteed and backup flows are supplied, and that things can be inspected and changed out easily and safely, and that people can see what it's doing and monitor its performance. So the second stage is the manufacturing stage, and the first step of that stage is manufacture itself. So that's taking the copper and the pipework and making the things that have been designed, the launders, the tapping blocks, the splash blocks, etc. And we use only hand-picked strategic partners. We rely on their specialised expertise and equipment, and that's very extensive, and they work to our stringent specifications. In the manufacture stage, the second step is inspection and testing. So we have rigorous inspection and testing routines. We remain actively involved in that process, and all results are reviewed to ensure that components are fit for purpose. So in the integration stage, there's 4 steps, and this is really about things where we've gone over and above just making the copper elements to make the installation and the operation of the system seamless. So this is all the peripheral things that we do in a project. So the first one is transport and handling aids. Often these blocks are hard to handle. They're heavy and sometimes odd shapes. So we'll look at the transport and handling to make sure that they can arrive at site undamaged and that they can be handled safely. That saves time and prevents downtime, which means your furnace can get back to productivity sooner. In the integration stage, the second step is installation aids. So similar to the transport ones, often special jigs and equipment is needed. Often installation, it requires to work in tight spaces and limited access. So we work through the site issues with the plant owners and make sure those issues are identified and planned for. So for example, the splash block you see in the picture there needs to go about 30 meters lower than it is there and be installed in the belly of the furnace. So even just getting it through the plant can be an issue, and there's massive safety issues handling heavy blocks like that. So you need to plan to mitigate the safety risks, and you need to plan to minimize the install time. Again, it pays to communicate and bring everyone into that ISASMELT success zone. So Glencore Technology always offers on-site technical services at this stage of the project, and it's almost always taken up by the customer because it's a critical phase. In the integration stage, the third step is system commissioning. So that all the process and mechanical parameters need to be checked and set, and most importantly, benchmarked for reference during operation. And again, we always offer to our customers in projects on-site technical services at this stage, and we always find that well-planned commissioning pays off big time in more rapid startups. It's a really critical step. Then the fourth stage is in the integration, in the integration stage, the fourth step is operational monitoring. So that means that just being aware of any plant changes, you might have a change in feed or some other change, and that can bring about a change in the performance of your cooling blocks. So that needs reviewing and checking against that benchmark data and addressing any deviations. So we do offer this, and many sites take us up on technical services on site, but more frequently this is offered remotely from our Brisbane office, and issues, problems, data can be reviewed and new benchmarks set if need be. So this is a summary of those 3 stages and 10 steps: the design, manufacture and integration, and the model with the ISASMELT success zone. We have the people in all those spheres to provide what you need to deliver a project with implementing copper elements. But it is recommended that some of the plant owners team get into that team and really buy in so that they can bring home the benefits of that. So we don't just design copper elements, we do all 10 steps in that process. We don't just manufacture, we do all 10 steps. And we find that's beneficial because we can get the seamless operation and the consistency by doing that. So that's how we implement typically an ISASMELT project, but that's also the same principles are applied to operating sites for Glencore and other customers around the world on brownfield sites that are already in operation.